Hello, everyone. A very good morning to all of you. Hope everyone is safe and healthy wherever they are. I welcome you all in today's session and on making sense of COVID-19 forecast using data and science. On behalf of Dolphin PG Institute of Biomedical and Natural Sciences, I Anshli welcome our guest Dr. Gautam Menon sir from Ashoka University. Welcome, sir. I welcome Dr. Arun Kumar, Director, Dolphin Institute. Further, I would like to welcome Sir Dr. Ashish Raturi, Head of the Department Physics, Dolphin Institute. I welcome all the faculty members, students, researchers, and all our viewers who are watching this through YouTube. And to begin today's session, I would like to invite Dr. Arun Kumar, sir, Director of Institute, for welcoming our guest. Please, sir.
Thank you, Anjali. A very good morning, ladies and gentlemen, and a warm welcome to all the participants on behalf of Dolphin PG Institute of Biomedical and Natural Sciences, Dehradun. It's my privilege to extend a very warm welcome to our distinguished speaker of the day, Dr. Gautam Menon, Professor of Physics and Biology at Ashoka University, Sonipat, and Adjunct Professor at Tata Institute of Fundamental Research, Mumbai. Professor Gautam is going to speak on making sense of COVID-19 forecast using data and science. Dear students, in a matter of months, coronavirus, what we actually call as COVID-19, has brought an unprecedented crisis to the human race across the national boundaries. Many nations around the globe have decided to shut their population until the situation normalizes. Terms like first wave, second wave, and impending third wave have become household phrases in our country, and of course, they guide the government, industry, hospital, educational institutes, and common men and women like me and you to determine a whole lot of policy paradigms. I think the whole media is busy reporting on second wave and the possible impending third wave. In these tough times, the world needs to make decisions rapidly and change equally fast to ensure that the damage is minimized by taking timely actions to counter the pandemic. You would agree with me that a reliable forecasting system could be our best guide. I think it's common curiosity in minds of all of us that after all, how these waves are determined and forecasted like our daily weather reports. Young friends, we are lucky to have Dr. Menon with us today, who will be addressing the science behind these critical estimates of the COVID-19 pandemics across the globe. It's always a pleasure to share a few things about our institute and its dynamic chairman, Shri Arvind Gupta. Friends, he realized that the demand for qualified youngsters in the field of natural sciences is perennial and ever enlarging across the globe, especially in past decades due to rapid industrialization. At the same time, the third world developing countries are on the verge of population explosion and are vulnerable to situations we are facing today, thus need more and more health care. Recently, WHO has laid great emphasis on generating more biomedical professions to cater to the needs of rural population in these countries. He knew that the above goals can be only be achieved by educating more youngsters in this field. With the above objective, the Dolphin PG Institute of Biomedical and Natural Sciences, Dehradun, a self-financed postgraduate college, was established in the year 2002 with dedicated efforts of this outstanding gentleman. Initially, the college started with undergraduate programs in forestry, medical microbiology, medical lab technology, and physiotherapy. Subsequently, postgraduate programs in medical lab technology, microbiology, biotechnology, pharmaceutical chemistry, biochemistry, and physiotherapy were introduced. Diversifying further, undergraduate programs in agriculture and horticulture, along with postgraduate programs in industrial biotechnology, chemistry, zoology, botany, forestry, agronomy, and physics was introduced. Currently, we have an enrollment of approximately 2,700 students in the above programs. The college feels pride in sharing with you that during academic session 2019-20, four girl students of the college secured Overall, first position with gold medal in the university in MSc programs in biochemistry, biotechnology, microbiology, and pharmaceutical chemistry. Our strength lies in over 100 highly qualified, dedicated, and experienced faculties from reputed Indian universities and many renowned medical and paramedical colleges, with a backup of more than 40 fully outfitted laboratories for different streams. The institute is affiliated to HNB Garhwal Central University, Srinagar, Uttarakhand, and is approved by the Ministry of Health, Government of Uttarakhand. We are midway in the process of second cycle of accreditation by NAC. I wish each one of you would be tremendously benefited by being exposed to the science of COVID 19 forecasting today by none other than Professor Gautam Menon, our distinguished speaker of the day. Thank you all. Jai Hind.
Thank you, sir. And now I request Dr. Ashish Raturi, Head of the Department Physics, to please introduce our guest to the audience. Please, Dr. Raturi.
Thank you, Anjali. A very good morning, everyone. It is really a delightful to have all of you here today, and it's my privilege to introduce today's speaker. Before introducing our guest, I would like to quote Yuval Noah Harari, a famous historian. I quote unquote, "We study the data and science not to know the future only, but also to widen our horizons to understand that our present situation is neither neutral nor inevitable, and that we consequently have many more possibilities before us than we can imagine." I unquote. The same analogy we want to extend and expect from today's lecture. Dear participants, as you know, the Department of Physics of Dolphin Institute always brings to you the intellectuals from across the globe for enriching our students' knowledge base in several ways. And in this continuation, today we have a cosmos personality from intellectual domain of this country. He is none other than Professor Gautam Menon. Professor Gautam Menon is a professor of physics and biology at Ashoka University. Prior to joining Ashoka, he was a professor with the theoretical physics and computational biology groups at Institute of Mathematical Science, Chennai, where he is the founding dean of the computational biology group. He is currently adjunct professor in the Department of Biology Science at Tata Institute of Fundamental Research, Mumbai, India. He completed BSc Honours in Physics at St. Stephen's College, Delhi, and MSc from IIT Kanpur, and PhD from Indian Institute of Science, Bengaluru, following the postdoctoral work at the Tata Institute of Fundamental Research in Mumbai, and the Simon Fraser University in Vancouver, Canada. He joined the Institute of Mathematical Science. His research work is spread over approximately more than 100 papers, covers a range of areas in both physics and biophysics. He has written several articles on the interference of science and society, as well as on the science policy. He was awarded a DST Fast Track Fellowship for Young Scientists in 2002 and the Swarn Jayanti Fellowship of DST in 2005. He was named a DSRC Outstanding Research Investigator in 2010. He was named an Outstanding Referee by the American Physical Society in 2012, as well as recognized as an outstanding reviewer of the UK-based reports on progress in physics in 2016. He was a visiting professor at the Mechanobiology Institute and the Department Biological Sciences at the National University of Singapore between 2012 and 2013. He just served on a scientific review committee of several international agencies, including the Human Frontier Science Program and the Wellcome Trust DBT Indian Alliance. He works on a number of biophysical problems, including nuclear architecture, axonal transport, collective cell migration, and the cell adhesion, all in the general field of the mechanobiology, the modeling of infectious diseases, and its implication for the public policy is a long-standing interest of his, while use the machine learning methods in clinical context is more recent one. Really, he's a foremost mathematical modeling expert for the infectious diseases in the scientific community of this country. As I know, amid this COVID-19 outbreak, he is very busy to figure out the pattern of the consequences and the possible solution to mitigate them. Despite being very occupied, he accepted our invitation, shows his strong commitment for the academia. Thank you, sir. So without any further ado, I would like to invite Professor Gautam Menon to deliver his talk on making sense of COVID-19 forecast using data and science, and request to our audience, if they have any questions regarding to subject, please go ahead and put them in our chat box. Definitely, Professor Gautam Menon will love to answer your particular queries. So I would like to invite Professor Gautam. Please, sir, now mic is over to you.
Thank you, Dr. Ashish, and thank you to the Dolphin Institute for this invitation to speak about COVID-19 and modeling. Let me share my screen. Can I confirm that you're able to see my screen, my full screen? So this is my, what I'd like to talk about is how to make sense of COVID-19 using data and science. I want to describe a little bit about diseases in the beginning. So this is an old picture of patients of plague in Bombay around 1900. So nothing very much has changed. You see patients lying on beds. You see doctors at the back. This is an old picture. So now you should be seeing my second slide. Please let me know if it's not moving between slides. But I just want to point out that diseases are very old. Smallpox, leprosy, malaria, and polio have all affected humankind since very ancient times, since 2000 years ago or more. Among the diseases that have been important to us in more recent times, in changing our history, I'll give you another example a little later, is of course the example of cholera and the example of plague. Plague has been extremely important in the history of the world in terms of the changes that it has brought, the social changes that it has brought, the changes in government that it has brought, and the fact that diseases can be important enough to make large-scale changes in society. That's something that you should remember. And here is a nice book by Chinmay Tumbe that looks at pandemics, different pandemics, not COVID-19, but the pandemics that came before that, the Spanish flu, which I will tell you about, and how they shaped India and the world. The most important idea when you think about disease is something that now since all of you are undergraduates in science or postgraduates in science or have some knowledge of science, you may have forgotten about the importance of this idea, the germ theory of disease, which says that infectious diseases are caused by very small organisms or microorganisms. And these are typically bacteria or viruses. And the ideas behind this go back many, many centuries, as Galen from the old Greek tradition. There are Fracastoro, Pasteur, Koch in the more modern times, 200, 300 years ago. But the idea that diseases could move between people because you could transfer a microorganism from a person to a person is very, very central to how we think about diseases nowadays. Here's one example of the microorganism, the virus that causes COVID-19. This is called the SARS-CoV-2 virus. And it has this shape, it's a sort of circular shape. It has these little spiky things that come out of it. This is called the spike proteins. And you can see this is a fairly large virus by standards of the virus, but it's still too small to be seen by an ordinary microscope. Certainly not with the naked eye, not even with an ordinary microscope. You need an electron microscope in order to see it. And these little things that stick out of it, because of the shape of these things, it look like a crown if you took a cross section of this. This is why it was called a coronavirus, with the word corona meaning crown, derived from the root word meaning crown. So that's what a coronavirus looks like. This is an idealization, artist idealization, that is put together from taking electron microscopy images, try to analyze them to look at the structure of the virus. When a virus enters a cell, so there is a cell of the body in the extreme left, you can see the virus is being much smaller and coming in. The virus enters the cell, it removes its outer parts so that it exposes only the genetic material inside. That material is then treated. It gives rise to other proteins that make up the virus itself. These proteins are then encapsulated. More of the DNA or the RNA is created. And finally, you have whole intact virus particles inside. And then at some point, they burst open the cell or they leave the cell in some way, releasing a large number of viruses, which can then go and infect other cells. Sometimes the cell is destroyed, but often it just happens that through a process of budding that these virus particles leave. The body recognizes that the virus particle is foreign to it and mounts its own immune defenses to deal with it. But this is how the process by which a virus invades a cell, as the virus that I showed you in the previous slide. We know many things now because of our study of infectious diseases of how bacteria and viruses move between human beings, either directly or indirectly. The direct motion of bacteria and viruses between humans happens through direct contact, for example, a handshake, but it can also happen through surfaces. For example, if you touch a doorknob, a door handle, somebody comes by and touches it later, the bacteria and viruses that have moved, that you have put from your hand onto the doorknob, can be taken in by the other person. So that's an indirect contact. The third way, which is very important for COVID-19, is through droplets. Whenever you breathe, whenever you shout, whenever you speak loudly, you release small droplets from your mouth. These droplets, if you're infected, can contain a virus particle surrounded by mucus, and this can float around in the air. They're very, very small. Again, can barely be seen through a ordinary microscope. But then someone coming by can then inhale it or ingest it, and that is one way of transferring a virus from one person to the other. The smaller the droplet is, the longer it survives, the more easy it is for someone who comes by later or for the droplet to move somewhere else. And then someone who's some distance away, maybe about 10 meters away, 5 meters away, can ingest those droplets and then again fall prey to the disease, again be infected by the disease. So it's important to remember that COVID-19 is transmitted through droplets. And because of the droplets, that's why the importance of ventilation and the importance of mask wearing comes. Mask wearing protects you from some of the bigger droplets from entering. It doesn't protect you for a long time, but it provides some measure of protection, especially if you double mask. But even more important is to have well-ventilated areas to make sure that you are not in small enclosed spaces that are badly ventilated, because anyone who is infected there can leave their droplets in that area. Because it's not ventilated, the droplets will not move out or be diluted. And because of that, if you go back in, if you're susceptible and you come into that room, you can ingest those droplets and then you can fall ill. The sources of diseases is interesting, and some diseases come to us from animals. Some diseases, of course, are completely human diseases. For example, let's say measles or plague, etc. That plague also comes from animals, so that's not a good example. But certainly things like influenza or measles and so on are diseases that transmit between human beings. But there are other diseases that really come to us from animals that are their natural hosts. For example, bats or poultry. Such diseases are called zoonotic diseases or zoonoses. Okay, so these normally the bats, the poultry, the camels, etc., are all natural hosts for their viruses, and bats are very good natural hosts for many viruses. But there comes a time occasionally when the sequence of DNA or RNA inside the virus changes in such a way that it becomes effective at infecting human beings. That is what is called a spillover event. And when you have a spillover, you can have something that naturally infects animals moving to naturally infecting human beings and transmitting between them. COVID-19 is one such spillover event. It defines one such spillover event where the virus moved from a bat, presumably to some animal, maybe a pangolin, and from there to human beings. This is important because a large number of diseases nowadays are called zoonotic diseases that spread between animals and people. So 3 out of every 4 new diseases come to us from animals. This is why it is important to worry about how humans and the environment interact with each other to protect the environment as far as possible. This is a field called disease ecology. So thinking about disease ecology is extremely important in the long term to understanding how to prevent diseases like this that come from animals from coming and infecting people. So as I mentioned earlier, we are surrounded by bacteria, viruses of all sorts. Our immune system is what protects us from these. For example, protects us from influenza, we've got it recently, from other types of diseases, and any sort of prior contact with whatever is infectious, with the microorganism that is infectious, the bacterium or the virus. It gives you some level of protection because your immune system remembers that it has seen this earlier. What vaccinations do is to make the system ready to arrange to fight against any new virus or bacterium that comes and infects it. So the vaccinations prime the immune system to do this, which is why vaccinations are very important. This is important to state here because COVID-19 is what is called a new virus. Your body has not seen it before. So there is no prior contact that you have. There is no preparation that your body can have, which is why even though COVID-19 is overwhelmingly a mild disease, most people will be very mildly affected by it, and only small numbers of people will have serious illness or will die as a consequence. Everybody's equally at risk because all of us have exactly the same amount of immunity against it, which is basically to say no immunity at all. This is a virus that our bodies have not seen earlier. We have seen nothing like it. Let me make the distinction between an epidemic and a pandemic. An epidemic is a sort of local outbreak of disease. Maybe it's a state of Kerala or Tamil Nadu or Uttarakhand, or maybe parts of India, but not moving outside India. But a pandemic is a disease that spreads over multiple locations, multiple countries, multiple geographical regions. So that is what the meaning of the word pandemic is. And COVID-19 is a pandemic. Let me tell you a little bit about the classic pandemic in our history, and that is called the Spanish flu pandemic. And here is a picture of the Spanish flu. The Spanish flu swept across the world between January 1918 and December 1919. So a little more than 100 years old. Now we're around 2021. So if you look at this, it's a little larger than 100 years ago, but this was the most important pandemic of the last century, where like COVID-19 will likely be the most important pandemic of this century. And you can see this large ward of many people lying down together and waiting for the doctor to look at them. Spanish flu infected about 25% of the world's population at that time. So roughly 500 million people, if there were 2 billion people in the world at that time. And it killed about 30 to 50 million people. And of them, a large fraction died in India alone. So the effect of the Spanish flu influenza, even though it was a pandemic, it spread across the world, the effect was largest in the country of India. About 15 to 20 million people died in India alone. And if you look at our population at that time, it's around 5 to 10% of our population at that time. So if I look at the equivalent of 5 to 10% of our population now, that's the equivalent of 70 million deaths in India now, is what the equivalent of that death toll at that time would have been. So far, we have seen only about 0.3 million official deaths. Maybe the unofficial number is about 3 or 4 times that, but they're still very, very far away from 70 million deaths. So you can imagine the scale of what might have happened if you had 70 million people dying over a period of about a year and a half, 2 years, rather than just the 0.3 million to 0.5 million that we expect may have died in India. I will now tell you a little bit about COVID-19 and the history of COVID-19. So let me just go back and remind you that the origins of the COVID-19 pandemic were at the end of December 2019, when the World Health Organization was informed of a strange outbreak of pneumonia whose cause could not be predicted, could not be told at that time, in the city of Wuhan inside China. Wuhan is in Hebei province. Wuhan is a very important Chinese city. It's the 7th largest city in China with a population of about 11 million residents. Just to give you some idea what that number means, the population of Delhi is around, let's say, the whole NCR region is about 18 million to 20 million. Bangalore is about 7 million. Bombay is about 12 million. So you can see that this is a fairly large city by any standards. So hospitals in Wuhan had begun to see cases that looked like pneumonia cases during all of December 2019. And finally, this disease was diagnosed as some sort of viral pneumonia. But which virus was the question? Pneumonia has both a viral and a bacterial form. The bacterial form is usually more common. And over here, the quest was then to try and understand what was the virus that was giving rise to this large number of cases that they began to see in December of 2019. By the January 13th, you had seen the first case outside China. By 19th of January, you had seen the first cases in China, but outside Wuhan. Then 20 to 21st of January, Japan, South Korea, US, Taiwan, Hong Kong. You can see how fast it has actually spread. And on the 23rd of January, there was a whole lockdown inside Wuhan. So here's a movie of the spread of COVID-19. Let's just sort of see how it has moved and spread over the first 3 or 4 months of 2020. So let me just start it off. And now you can see the location of Wuhan. You can see the infections there, and the sizes of the circles that are drawn represent the sizes of the number of cases there. You can see how it goes from 15th, 16th, 17th of January. That's a ticker on the right-hand side. So there's Thailand, there's Japan, there's Singapore. It moves now to Mongolia, then the US and Canada, then Europe, then Russia. And you can see what this means by a pandemic, how fast it has spread across all of these many different regions of the world, how these circles are getting bigger and bigger. The number of cases are rising even more steeply and steeply as time goes on. So this very, very fast increase in the number of cases is what tells you that this is a pandemic that spreads very fast between people. Now you can see that South America has been affected. Various cases have been reported in Africa, Australia. These circles are slowly growing larger. So much of Europe by this time had already been hit. And now we're only on the 8th of March, which is about 2 weeks or 10 days before the Indian lockdown itself. That's what the Indian numbers look like. You can see the slow peak that we had around the 15th of September of last year, of 2020. And then the cases came down for a long time. And then you saw this huge peak that you can see over there, which is a second wave peak. And that is the wave that has hit all of India, including your state as well as the state where I am currently. And the number of cases rose to a maximum of close to 410,000 compared to the earlier maximum of about 98,000. So you can see the relative sizes of these peaks and the speed at which the peak actually went up for the second round. This is the situation of the world right now. Around 172 million cases have been seen across the world. So 172 million is 17 crores, 29 lakhs, 80,332. Of that, the US has seen the largest number of cases and the largest number of deaths, close to 600,000 deaths. India has seen the second largest, in between just a little more than Brazil now. It was earlier less than Brazil. India has seen 28 million cases so far, and Brazil has seen about 16 million cases so far, and the number of deaths are also described over there. So right now, while cases in the US and Brazil are going down slightly, India, all these cases are going down. There are brief resurgences up and down. Japan is seeing an increase in cases. Some of the Far East is seeing an increase in cases, but these are essentially the worldwide phenomena that you can actually see. And you can see that even some smaller countries have had an impact that is disproportionately large compared to their populations. And that's an interesting thing that you can see if you look at all of this data. This is how it's been across India. This is a little crowded, this particular slide, but you can see that the number of cases in Maharashtra have been the largest so far in the country. So Maharashtra, Karnataka, Kerala, Tamil Nadu, all of these have been very badly hit in the pandemic. So this is organized by the cases. So total number of cases of India, as I said, is around 28 million. So Maharashtra is about 5.8, 2.6 for Karnataka, Kerala, Tamil Nadu, Andhra. Much of these is really the South Indian states, the four major South Indian states of Karnataka, Kerala, Tamil Nadu, and Andhra. And whereas surprisingly, a very, very big state like Uttar Pradesh is not, or Bihar, is not seeing as many cases as you might have expected. In fact, case numbers are actually fairly small compared to these other states. So then there is a question, is it just because cases are not being recorded correctly? Are there many people who have not been tested for the disease, whereas Kerala, Maharashtra, Karnataka may just simply be doing a better job of testing people on making sure that they get to hospitals and keeping track of deaths inside? So the question that sort of comes up whenever you think about data that looks like that, the peak and the coming down, is if I showed you data at various times, if we had looking at the way the cases were increasing between here, 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 would it be possible to look at and understand the full trajectory of the pandemic? What might happen 2 weeks later? What might happen 4 weeks later? So the people who work in modeling worry exactly about questions like this, and they try to relate this to the data that they have. So I want to tell you a little bit about that. But first, before that, let me tell you about why one should model. And as you can see, one reason to model is to know what to expect in the future and what to plan for, even though this may be a worst case scenario. The second reason is to decide how to intervene and when to intervene and what your interventions will actually do. For example, should you lock down a city? Should you impose a local quarantining? Should you be even more strict about masks? Can you afford to open up shops? All of these questions are questions that rely on the nature of modeling of that disease. There are many complications with modeling, and one model thing is that I drew a smooth line here, but the actual data for the number of cases, etc., is a much more jagged sort of structure like that. That reflects natural random variation. Not every exposure to someone who's infected leads to an infection. Not all infections lead to a disease. It could be mild. And of course, there are many other reasons why the data looks noisy and not like a nice smooth line. People are not testing enough. There are delays between the reporting of the results of a test and the test being taken. Data is being hidden or suppressed in some way. Or the data is just inaccurate for various reasons. It is just misplaced or copied badly from one place to the other. So these are much harder to account for, to understand where the errors in the data might actually be. So now I will tell you a little bit about modeling, just as background. I will tell you about a model called the SIR model, which is very fundamental to thinking about disease. So the SIR model is a disease in a population of individuals. So every individual is different. You are different from me. But as far as the disease is concerned, there are three broad categories that we fall into. We can be susceptible to the disease, we can be infected by the disease, or we can have recovered from the disease. So these three categories, the S, the I, and the R, go into the name of the SIR model. If you're susceptible to the disease, you've not been exposed to the disease, you're not infected by the disease, but you could become infected in the future. If you're infected in the I category, you can be infectious. You can transmit the infection to other people. And if you're recovered, you have recovered from the infection. It will not bother you anymore. if you have a long-term immunity to that. So now the idea is to put each of these people labeled by S, I, and R into different boxes or compartments, and you label these compartments S, I, and R. And then the process of understanding what happens to the disease is just to understand the flows between compartments, how susceptible people become infected and how infected people recover from the disease. So the fundamental quantity to model is just a number in each of these compartments. Now, if you ask, what does a virus do once it comes and infects you? So here is time on this axis. Here is the amount of virus inside your body, or viral load. And you can see at the start of the infection, the viral load begins to build up. But there is a period where it's building up, but you show no symptoms at all. Or you show symptoms only much later. So now there's the point at which the virus is building up. But beyond the point, it becomes possible for the virus to be transmitted to somebody else. And that's the point where you become infectious to someone else. That's your period of infectivity. So that virus goes up, and then your immune system is constantly fighting against it. By the time it reaches its peak, the immune system has managed to mount a defense against it. And then the virus comes down. And once it reduces beyond a certain point, you're no longer infectious to anybody else. When your symptoms start, your symptoms are really tied to your own body's response to this, your own immune response to this. So the symptoms can start somewhat later. So the interesting thing about COVID-19, as also with influenza, as also with other similar diseases, is that you can be infectious before you show symptoms, which is why it's very hard to deal with COVID-19, because it has this very unusual and interesting property. So we can put an additional little column inside, an additional little compartment to define people who are exposed to the virus. So the virus is growing within them for a certain period, but they're not infectious yet. So that is a susceptible, exposed, infectious, and recovered, or an SEIR model. And SEIR models are the simplest models that people have used to understand COVID-19. I can take that description and then write it down in mathematics. So the mathematical description of how susceptible people become infected, how infected people recover from the disease, is in that set of equations to the right-hand side. And these very classic and important set of equations was first written down by two Scottish mathematicians, Kermack and McKendrick, and they contain all of the details that might be important to understanding what diseases do. So you can take those equations and write the answers to those equations. And there are three lines here. One is a line for susceptible, one is a line for infected, one is a line for recovered. The susceptible numbers come down all the way like this and then become a small number. The infected numbers go up and then come down. So that's a standard peak that you might have seen in the data. The Indian data shows you a peak and then a coming down. And the recovered people just go up and they saturate. So the susceptible, infected, recovered model, or the SIR model, has only one peak. So one question is, where do multiple peaks come from? And what is the understanding, biological understanding, and the understanding from models of where multiple peaks might come from? The questions here to ask is, will the disease spread? How many people will be infected by the disease? And all of these answers depend upon one property of those equations that is called the basic reproductive ratio. The other word for it is R0 or R0. So let me tell you a little bit about what that is. So the reproductive ratio is the most important characterizing feature of a disease. And that tells you, of an infectious disease, and that tells you that if I have the infection, on average, if everybody around me is susceptible to the disease, how many people do I infect? So for every disease carries with it a reproductive ratio. For Ebola, that number is 2. For swine flu, that number is 2. For HIV, it's 4. For smallpox, it's 7. For measles, it's 18. So if I have measles and everybody around me has not had measles earlier and has not been vaccinated against it, I typically will infect 18 people before I recover. If I have smallpox, I will infect 7 people before I recover. So that's some indication of how contagious the disease is, how well it passes between person and person. Because of this fact that each time you're infecting more people, that I infect 2 people infect 4 people, because each of them can infect 2 people, each of them can again infect 2 people. So at 1 to 2 to 4 to 8 to 16 to 32, etc. This is called an exponential growth, because the numbers can get very large over a very short period of time. So the interpretation of an R greater than 1 is that at every step, more and more people are being infected. So that is an epidemic. It's spreading across the whole population that you have. If R is equal to 1, on average, I infect 1 person before I recover. So this is called an endemic disease, where it never vanishes from the population, doesn't go up, doesn't go down. For R less than 1, on average, I infect a smaller number of people the next time. So if I have 10 people infected, maybe it goes to 5 people, maybe it goes to 3 people, maybe it goes to 1 person. But that's a signal that the disease is dying down. So the way of thinking about it is that the reproductive ratio, and anything that I do to change the reproductive ratio, will really change for me the course of the disease. So here is only the infected that I draw here for different values of the reproductive ratio. For a high value of the reproductive ratio, the number of infected goes up very sharply and then comes down. As I reduce the reproductive ratio, it flattens and becomes broader until a smaller reproductive ratio has one gentle peak and then it comes down here. So by changing the reproductive ratio, I have managed to reduce a peak number of people who are infected, right from about 65% to a number about 10 to 15% at the smallest values of the reproductive ratio. The SEIR model, as I said, is a more complicated version of the simple SIR model. That's the way we write it out in terms of the different compartments, S, E, I, and R. So I can now go back and look at the reproductive ratio and say, ask these questions. How many people will be infected? And you know that because you know the shapes of those different curves that I showed you. So the answer is that it depends upon R0 or R0. The larger that R0 is, the larger the number of people who will be infected at the end of the epidemic. It also answers the question of why should you vaccinate against the disease? The answer is that by vaccinating people who are susceptible, what you're doing is reducing R0. But you don't need to vaccinate everybody because there is a certain limit below which R0 crosses 1. Once R0 crosses 1, the disease will die out on its own because each time it becomes harder and harder to find somebody who's susceptible in order to infect. And there's an exact relationship between the threshold of people, the number of people you have to vaccinate, and the R0, which is the form there. It's 1 minus 1 by R0. So for Ebola, for R0 equal to 2, it's enough to vaccinate 50% of the people. For measles, if with R0 equal to 18, you have to vaccinate 95% of the people, which is why you have a measles vaccine right from the point where you're a child. It's one of the earliest immunizations that you're given. The interpretation or the understanding of R0 is the following. It's a multiplication of three quantities together. One is, what is the probability of infecting somebody? So that is called a tau, the Greek letter tau there. So given a susceptible and infectious person, with what probability does the disease move from the infectious person to the susceptible person? Is it transmitted? The second is the average rate of contact. How do you control, how many people do you meet per day whom you could potentially infect if you were infectious? And the third part is, how long do you remain infectious? Which is, if the longer you remain infectious, the easier it is to pass the infection on to people, and the more your reproductive ratio will be. And that suggests how epidemics might be controlled. So the first way is to reduce transmissibility. So for example, if you have vaccines, you're preventing people from transmitting the disease from it. Antiretrovirals, which reduce your viral load, for example, in AIDS, is another way of reducing the transmissibility. The second most important thing is to reduce contacts. So isolation, quarantine, health education, etc., reduces. So even masks reduces the transmissibility, but any sort of lockdown and so on will decrease the contacts between people. In quarantining people who are suspected of being ill will reduce the contacts between people. Other health education programs will tell you that, look, don't interact too much with people, interact only in small groups of people who you know, and that helps. The third point, of course, is somewhat harder to do here, but that's just to reduce the length of the infectious period. So that's where antibiotics or antivirals or other types of treatment actually happen. And any way of boosting your immune response will also help to reduce the length in which you remain infectious. And all of public health concentrates on these three main aspects of trying to reduce R0 from its initial value. So I work with a bunch of different models. So one set of models that we worked with is models developed by a group called the Indian Scientists Response to COVID-19, or the ISRC. So we have a website which has a lot of useful information. This is information on how to deal with the pandemic, how to bust myths around the pandemic, how to bust hoaxes around the pandemic. A lot of public engagement that we've created in multiple languages. There are languages in Hindi, Bengali, and Urdu. All languages we have, about 18 to 20 different languages. We have material about COVID-19. So I will encourage all of you to go to the website of the ISRC and see if there is any way where you can help use the material that we have prepared there, which are used for ordinary people, for the public, for scientists, for healthcare professionals, and see if you can contribute to our efforts. So on this, there is a web page that describes the simulations that we have done. So there are multiple reports that we have written on our simulations. The simulations are for a somewhat complicated model, and that's what the different compartments, there are many more compartments in this model. So there's a susceptible compartment called S, an exposed compartment called E, and then the exposed compartment bifurcates into an asymptomatic and a pre-symptomatic compartment. Asymptomatics are a big feature of COVID-19. Many people who contact COVID-19 will not know that they have been infected because the symptoms are very low or non-existent. And these asymptomatics will typically recover directly. If you're pre-symptomatic, you can either be mildly asymptomatic, in which case you still have symptoms of COVID-19, a bad cough or fever for a few days, but you will automatically recover. The serious cases, again, are when pre-symptomatic becomes serious. Serious cases are those that require hospitalization. So from hospital, you can either recover or you can die. That's the last box over there. The H is the hospitalization compartment, D is the death compartment. So that's how we can keep track of what are the does a model predict for the number of people in hospital, the number of people who've died, the number of people who are asymptomatic, etc. So we can take this and make this into equations just as I did this. So we've done this for the first wave of COVID-19 of last year. We have lots of results, but I will tell you only about the results for the first wave. Remember that it started, our first case was on the 30th of January 2020. The wave had finished by about the middle of February. The number of cases had begun to plateau to a value a little larger than 10,000 cases. And the peak of the cases was around 97,860, and that happened around the 15th of September. So here, as of course, in different cities, for example, Mumbai and the infected and deaths, etc., they were somewhat different. Delhi behaved differently from Mumbai. Mumbai saw essentially what looks like 3 peaks over here. And you can see the comparison of the projections that we have. The central darkest little band is the most important band, and you can see that even though cases and deaths are all over the place on a day-to-day basis, they roughly follow the description that we have here. For all India, this is our model fit. If you sort of see the line that is going through the center point of the dark region, the 95% confidence interval region, you can see how we pick up the trends in the cases as they change, even though this data is actually fairly noisy in terms of the real cases. If you ask how many people have been infected in India by the end of the first wave, that's another thing that our calculations can answer. And the answer is we expect about between 30 to 40%, more like 40% of Indians have been infected by the end of the first wave. And that's important because you want to ask how many people have some level of protection against the disease as you go forward because they have had a prior infection. The other models I work on are models called network models and agent-based models. So a network model is where you try to understand the relationships, the social and the physical relationships between people. So both of these are what are called individual-based models. They're individual-based models of a somewhat different type. Networks answer different sets of questions from the agent-based models. So let me tell you a little bit about what the network model is and what they've been doing. So here's how to think about a network model. You can have people in a large number of homes. For example, in your city, in Dehradun, you can have people in homes with 5 people in it, 3 people in it, 2 people in it. And we have some idea of roughly what is the number of people in a home. You have people who go to work, so there are workplaces. Some people stay at home. There are also hospitals, and workplaces could be very general. They could be schools, they could be factories, they could be small offices. And you can model how people go from home to workplaces, workplaces back to home, etc. And how, if they fall ill, they can go from workplaces or home to hospitals and then come back. And over here, you can label each person as a susceptible, infected, recovered, etc., and then keep track of them. But in models like this, you can now prevent people from going to work if they're infected. You can impose isolation, you can impose quarantines, and all of this helps to now understand what happens as you increase the amounts of testing of your population to figure out who's infected and who's not infected. So we were working on this because we were trying to answer the question of how do you combine the rapid antigen test with the RT-PCR test. The RT-PCR test is an accurate test, but it takes 24 hours to get you a result, sometimes even more. And it's a delayed test, and it's also a more expensive test. The rapid antigen test does not work so well. It only works 60-70% of the time if you're actually positive to give you a true positive. But on the other hand, it's cheap, and it's also available instantly. Within 15 minutes, you have the answer to a rapid antigen test. So you can make this network of people at home and work, and these lines connect the same individual at home and their workplace. And you can ask, how does disease spread across this network? So you can look at the 20 days, 80 days, 160 days, and the colors have changed. The blue, the red color is susceptible, infected is the green color. And you can see how they map onto these different pictures that here. And here the idea is that you can also look at within these networks what is happening and how networks themselves change the nature at which disease actually spreads. The second problem that I was thinking about that we've been really working on very hard is a very large simulation for disease spread in the whole Indian population. So the idea is there you model each person individually, and you can, even though you may not be able to do 1.3 billion people, which is 138 crore billion population of India, you can do a smaller number, which might be good for an entire state or an entire city. So somewhere between 1 and 100 million agents might be what you might be trying to get. In order to describe these agents, you need what is called a synthetic population for these agents. You want to be able to describe them what they are. So Ram Singh, age 26, studying here, this income level, this comorbidity, has diabetes, doesn't have diabetes. You want to be able to put in information like that. That is obtained from various sorts of surveys, various sorts of statistical methods to try and reconstruct this. In the case of COVID-19, with an agent-based model, you can put in different variants that come to infect the population, various non-pharmaceutical interventions, as they're called, which basically means lockdowns and shutdowns, etc. Changes in behavior, economic decisions that people make, because you know what their economic status is. So here's one picture of some of the data that goes into the synthetic population. For example, each agent has a unique ID, they have a unique age, they have a home location, they have a height, they have a weight, they have some pre-existing conditions, they have you have the latitude and the longitude of the home locations. So all of this is made up data. It's made up in order to represent statistically the population that we want to study. So statistically, the population of Pune or the population of Bombay or the population of Delhi. So this is for the population of Pune, about 3 million people, where we have detailed reconstructions based on population densities of where people might be assigned to stay. And from here, we want to take this and simulate how disease spreads within the population. So one thing that we could do, that we did do, was to look at multiple variants. So you can look at the population of Pune of 3 million. That also had this nice sort of first peak and a second peak here. And this is how one says that after the first peak came down, suddenly at about 100 days after the first peak point, you have a new variant, the new variant of the virus that is coming in. And that gives rise to this sharp spike, the second wave spike that you can see. So this is a way in which you can actually predict what might happen or understand what might have happened in the past in terms of the effectiveness of the new variant and coming in. You can also do other clever things. You can put in vaccinations, you can put in reinfections, you can put in effects of new variants. So this is just at different reinfection rates. Suppose I have 10%, 20%, 30%, 40%, 50%. If I allow for reinfections, how much must that curve go up? And what is the exact relationship between what was seen in the data as well as what was seen in these simulations here? So how high was the second peak with respect to the first peak? And what does that mean? Are we looking at 40% reinfections, 30% reinfections? What was the effect of the vaccinations that were actually done? We can now hope to answer these questions using modeling. So let me finish up by making the following points. The first point is that as young people growing up and thinking about this, and probably with family, or you may also get into jobs that involve looking at data. So it's very important to have data that you can trust, and it's our responsibility in the collection of data to make sure that that data is useful. It's not made up. It's reported correctly and accurately to the best of our abilities. The reason is that any way understanding we have of projecting what might happen to the disease in the coming weeks or the coming months will rely on that data. So any mistakes in that data will go into mistakes into predicting what might be happening in the future. Some things we can adjust for. We know that many people who have COVID-19 are asymptomatic for COVID-19. So we can adjust for that when we make our comparisons to the number of cases that are observed versus the number of cases that are actually there. But we can't make up for very, very bad data for people who just do not report data, who make up data because they want to make the government look good. So that's why I want to stress again the importance of trustworthy data and to make sure that you understand that particular importance. This is important because data feeds into the modeling and modeling feeds into policy. The decisions about whether to shut down or not to shut down is a decision about how will you save lives best? How will you make exactly the sort of right choice between improving your economic state, because people have to work, people have to be paid. So there are economic considerations that come into there. But there's also considerations of health. So what exactly is a good public health strategy? To what level can you slowly open? What should you open last? What should you open first? These are all very important questions for people who think about policy. And this is all informed by good quality modeling. The last point, all of you are based in a state that is largely rural, has long gaps between the capital city and sort of a village very far away. And how do we look at questions of improving public health, not just in your state, but across India? We have now suffered through 2 waves of this pandemic, of the COVID-19 pandemic. Many people have died. We have seen cases or reports from Delhi and other big states and big regions of people dying because they didn't have oxygen in time. So that is something about a mismatch between policy which believed a certain number of oxygen cylinders should be made available was available, and the requirement. So in order to control the requirement, we have to understand the disease better, but we also have to improve our ability to provide health services wherever there is no reason why Indian rural areas should be worse off than Indian urban areas. And we have to worry very much about this asymmetry between the rural India and urban India, and make sure that we invest sufficiently in improving public health across our country. And this is a job for your generation to think about, your generation to do in the future, to try to address all of these questions. So let me stop there, and it's now spoken for about 45 minutes. Let me stop at this point, and I'm happy to answer questions that any of you might have.
Thank you, Professor Gautam, for this wonderful talk. And I think as you have as you have said in the beginning, that it's very general talks, and most of the things are very generals, and it's a good for our students. And some points you have touched in an advanced way related to modeling. Okay. So it is I have one thing is very interested in the last you have told, that is the trustworthy data actually. One before taking some questions from the audience, I would like to ask one question from my end. I'm very afraid to ask this one, but maybe you will get it. Uh, as in the first wave hit the India in last December 2019, that time there is no such kind of information of modeling or whatever. And when the second wave hit India, but before hitting with the second wave, most of the casualties happened after second wave. But the information of modeling that this will be now in the present way, we can say we can hear in the wave of media that now the third wave will hit the India. Okay, so at this time, the most of the informations in the public. But what happens in the before second waves? Because it's my assumption that maybe the agencies which are working on a model, they are not able to convey their message to the public health system that the second wave will hit the India. What's your insight in this aspect? Because maybe if they will inform, or if the this kind of information will be in a public health system, maybe the public health system may be in a robust way.
So that's a very good question, and so that the answer to that question is a bit complicated. One is, can you predict a wave? Could you have predicted the second wave in the first place? The answer there is no, because the second wave, as far as we know, came from a completely new variant of the disease that spread very rapidly. In fact, in the north of India, in Punjab, and they later Delhi and then across, it was a variant that came in from the UK, the UK variant. It's called the B117 variant, or the alpha variant currently is what the name is. Whereas in Maharashtra, it was a different variant. It was a 617 variant called the Delta variant right now. And that is a completely Indian variant that has now spread. In fact, that is probably the variant to be most worried about, because it has now displaced all the other variants because it spreads so much faster between people. It is impossible as a virologist, as a modeler, to try and understand what might happen here, because this is completely an accident of nature. The fact, no one can predict which regions of a virus will mutate. No one can predict if they mutate, will they mutate into become more transmissible or less transmissible. So all you can do is to have very good surveillance systems. Make sure that you test very regularly, look for an increase in cases, do genomic sequencing to figure out where the increase in cases, is it coming from new variants, is it coming from something else? And then based on that, you can do modeling. You can say, I'm seeing increase in cases, I'm seeing that there seems to be a new variant. This is how much more the variant is transmissible between people. What will happen in the next week? What will happen in the week after that? Because Maharashtra saw an increase in cases in really early February, by end of February, we should have had enough data to be able to project it to March, April, what would happen. And that would have been enough. But that is the point where modelers could have come in and said, we can now see it increasing. It is increasing so fast. This is what you can expect in March. This is what you can expect in April. Here is what the numbers should be. Please take efforts right now to improve medical availability of oxygen, improve number of ICU beds that are available. If you do all this, then you can hope to deal with that correctly. So that information, I think, was not accepted by government. This possibility was not accepted by government. And we did not have enough input from modelers to tell government that this was going to happen. And I think this is important, the fact that you must have both surveillance, you must have modeling that looks at that surveillance data in order to be very aware of what might be happening in the future. And for that, I think governments are responsible. Governments should make sure that they have a line they should not listen only to modelers who tell them what they want to hear. They should listen to many people together who give them many different views on this and integrate that into policy. It is not easy to be a government, it is not easy to make policy. But all you can do is to be completely honest about how you are making policy and take sure that you take input from people who do not agree with you, who think that something more serious might happen than what you anticipate. That's the only thing that I can suggest.
Dr. Gautam, if you allow me, sir, I have a very simple question. Sir, when will we have the normal days back in our lives? What is your prediction?
That is sort of hard to answer, but I think once you have about 50 to 60% of India being vaccinated, that I think is a point at which we can be much more relaxed than we currently are. Until we get to that point, we should be careful. So right now we're about... Sorry, sir. So we are now, I think about 22% of India has received at least one shot. Smaller number has received 2 shots. Once we get to about 50, 60% people having at least one shot and about 40% having 2 shots, then I think that is a situation where we can begin to go back to some sort of normal life. We should still be careful. Where possible, we should wear masks. We're now all used to wearing masks when we go outside.
No, that's okay, sir. But we can go out of the house. I'm asking as a senior citizen, we have our own engines. So you will not believe I have not gone out of my house for so many weeks now, months. I have not gone.
I can understand that. Yeah. So I would wait until some more people are vaccinated. I would wait until cases have come down. Cases are already coming down, so that is a good thing. But try to postpone it until more people are vaccinated.
Yes, we can have
about 50% would be about 50% would be
a benchmark of about 50 to 60% people are vaccinated.
Yes.
Then one can safely, with all the due precautions, we can move on.
Yes.
Thank you very much, sir. There are, sir, 1 or 2 questions, if you permit. Can I take them up on behalf of the
audience? Absolutely.
So there is one question: why do different viruses have such a wide range of symptoms that vary? Of course, it being such simplistic organism, even one virus shows a very varied range of symptoms. This is from another audience.
Oh, that's a great question. And I don't think enough is known that connects the nature of the virus because it's the complicated function of your immune system, which is extremely complicated. And the variety in human immune systems and the way they respond is conditioned by a lot of prior experience that they have, prior encounters, and the fact that you do have very different immune response in human beings. So you can have 2 people next to each other, maybe even brothers. One person will hardly have any symptoms, the other person will have to be hospitalized. So these are things that we do not understand very clearly. What is the relationship between the host and the parasite and the organism that infects the host, and how exactly the combination of immune response from the host interacts with the virus is not very clear. So this is a very interesting and important field of research that we should know more about.
Sir, one more question, sir. That is from one Mr. Apurva Chaube. He says, of course, good morning to you. And when the first wave hit India last year, I'm reading it verbatim, sir.
Yeah.
Last year, the number of casualties was low as compared to this year, the second wave. What can be the possible scientific reason for more casualties?
I think one reason is just more cases. That is probably the main reason. That the number of cases and the rate at which they went up was so fast that hospitals could not cope. There were people who came to hospital who could not have hospital beds, could not have oxygen. So many people died who should not have died under normal circumstances. If they had oxygen, they would have survived, but they were not able to give oxygen in time. And also you have, because if you increase the number of cases by a factor of 10 or 100, you increase the number of deaths also by a factor of 10 or 100. You are seeing more deaths, you are seeing more severe cases because overall numbers of cases are rising. That's one reason. The second, as I pointed out, is that the people who were sick went to hospital, because hospitals were overwhelmed, they did not have the treatment that they required in time that would have saved them.
So we can summarize it was because of more of the mismanagement of the health system. Yeah.
Yes, in 2 ways. One is mismanagement on the healthcare front of not making sure that hospitals were prepared, and the other was mismanagement in making sure that the cases did not rise very sharply, which we should have done earlier by other means.
Thank you, sir. The last questions are from one Mr. Ganesh Joshi. This is, of course, a very informative talk in a short period of time. I
Question, can we define this pandemic based on the value of R, just similar to epidemic?
Yes, we can, and we know what the value of R was for at the beginning of the first wave of the pandemic. It was around 2. That's how fast it spread. The value of R for the second wave is about double that, because the new variant is more transmissible between people. But R is a way that to characterize how it begins to spread. But once you begin to impose many restrictions, lockdown, etc., you don't talk about R0 anymore. You talk about an effective R. That effective R is usually much smaller than the true R0. But the R0 tells you how many people you're infecting. And we know the R0 value for the first wave and for the second wave.
Okay. There is one other questions I will take. That is, why do different viruses have such a wide range of symptoms that vary?
I think I answered this question.
Okay, yes. Okay. Yes, I think. So, Dr. Gautam, I think most of the questions we have covered, and thank you for being with us. And really, it's a pleasure for us that you are here. And one question, this is the last questions before we conclude this session. That being infectious disease model experts, what should be the robustness of this model? As you have said, the trustworthy data, and sometimes we segregate the models on the basis of the screening, on the basis of the validations, and on the basis of the which kind of how you can see the robustness of such kind of models.
Well, that's an extremely good question, and so one is that models should always tell you what the error bars are on the particular. I gave you very broad error bars when I estimated for you the number of cases in Bombay, in Delhi, in all of India, and the number of people infected. So those error bars, the 95% confidence interval, the 98% confidence interval, must always be specified, because that tells you about the range of uncertainties in the data that your calculation is coming up with. So that is important to specify. You can also, by comparing predictions for different things, if you just predict cases but you don't predict deaths or you don't predict hospitalization, then your model is a little weaker. So the more ways you have of testing predictions of the model that are made, the stronger you can be comfortable, the more you can be comfortable that the model is actually working and is giving you the right answers. But very important, as you say, Ashish, that you should specify uncertainties. Saying, here is my prediction, but this is the uncertainty around my prediction. So how unsure I am at the 95% confidence interval. A lot of modelers don't do that, which is a big mistake. We don't have that level of exactly as you said. We cannot be that certain of our model. There are uncertainties. There are errors. The data itself is not very good. So we have to try and account for all of that in the projections that we actually make.
Thank you, sir, for your valuable answers and your insightful talks. And definitely, we hope that in near future you will be physically present with us in our college.
I would like that very much.
Thank you, sir. So I think I would like to thank all Institute and all the audience who watched this. And at the last, I would like to request Dr. Professor Gautam that can you give one message to our biophysics students for their academic concern?
I'm glad that you are being scientists. I think you should, in your daily life and in the people that you interact with, you should emphasize the importance of evidence, emphasize the importance of science, emphasize the importance of data and of being honest to the data. These are things that you can do because you're trained as scientists and you're trained to understand the importance of all of this. So spreading scientific awareness in this country is an important thing that we have to do. We should understand what the value of science is. We should understand that people would like to know, and we should tell them what we can about it, make them interested in science, and tell them about the value of science. I think that's the only general statement that I can make to all your students.
So thank you, sir. Definitely, they will, keep your suggestions and your motivations to make their future bright in your. So we have to we will conclude this session. So I would like once again a big thanks to all. So now you are summing up it. Thank you.
Thank you. Bye.